Great. Yeah, so it's a great pleasure to speak here. So, yeah, I will talk about a recent paper which I posted in December. So, of course, lots of things has been learned about holography, and one of the fundamental relation in holography is this relation between the CFT partition function and the gravitational partition function. Say, if you consider CFT defined on some compact Euclidean manifold, and this Euclidean manifold can be very general, so it can be disconnected, topologically non-trivial, etc. Yeah, just anything you can put your CFT on. And then that's supposed to be equal to the gravitational partition function with this M as its boundary. Okay, and the relation, and there's a parameter relation between the CFT and the gravity fundamental one, which is in the CFT, there's normally n squared, which characterizes the number of degrees of freedom, then which is related to the 1 over g Newton on the gravity side. Of course, on the gravity side, yeah, so this relation is supposed to hold at the general quantum gravitational level, but normally we cannot actually access gravitational partition function at the, say, in the quantum gravity regime. So the most a useful version of this relation in practice is considered the semi-classical limit. So in the semi-classical limit, so the gravitational side, then we can approximate it by a gravitational path integral and doing center point approximation. And then in the Yang-Mills, in the CFT side, we take the larger limit. So I emphasize here when I take the limit should be understood as a symptotic expansion in the respective parameters rather than the strict limit. So on the gravity side, you should view this as a symptotic expansion in g Newton. And similarly, on the CFT side, should be considered as an expansion in 1 over n squared. Okay. And so the two sides should agree order by order in the expansion. Okay, so you can include, say, all the subleading term and exponentially subdominant terms, etc. All of them should agree order by order.
Recording in progress.
Okay, and but this relation, even though has been the foundation for holographic duality for the last almost 3 decades, but actually there are some problems with this relation, even from very early days of the ADS-CFT. So one problem is called the factorization problem. So this problem was already, recognized as a potential problem by Witt and Yao in 1999, and then Mendocino and Maus really sharpened it, significantly. So the idea is very simple. So let's consider M to be a disjoint connection, say, of two manifolds, say M1, M2. And then just by definition on the CFT, if you consider CFT on disjoint manifold, they just factorize into the product of the two partition function on the two manifolds. And this doesn't change. Say when you take an angle to infinity limit, then the partition function also factorizes in this limit. And then the gravitation, by definition, from this relation, then the gravitational partition function should also factorize. But in general, the gravitational expression does not factorize due to the wormholes. So you can have wormholes connect on the gravity side. You can have solutions with M1 and M2 as boundaries, but the full bulk of space-time is connected. Okay, so when you have such a connected space-time between the two disjoint boundaries, then gravity expression does not factorize. So, and so this poses a problem, and it means that the left-hand side cannot be equal to the right-hand side. So this problem is in some sense, quote unquote, solved in the JT gravity, in low-dimensional gravity, where it's shown that this JT gravity, which is defined by the gravitational path integral, actually is equal to the ensemble averages in some kind of ensemble average on the CFT side. And so in the ensemble average, then when you do the average on this disjoint manifold, then they don't, CFT side does not have to factorize anymore. And there's also indication that for pure ADS3 gravity, and which also have this kind of wormhole solutions, etc. Maybe that's also related to some random CFTs. Could be, you also have to do some averages, and then it's not factorized. But the story becomes much trickier when you go to higher dimensions. So what's special about those lower dimensional series is that in this lower dimensional series, you may be able to define your gravity theory just purely using path integrals, okay? Because there's no dynamical gravitational degrees freedom, and so you can just say formally define your gravity just using only path integrals. But this cannot be the case in higher dimensions. So we know that the higher dimensions, gravitational path integral cannot be used to define quantum gravity. And there are all kinds of issues, and we need string theory, etc., or string theory, M theory. So you need to go beyond gravitational path integrals, and the gravitational path integrals is just a device for us to do the semi-classical expansion. Okay, so this is for the higher dimension. And also for the duality from string theory, say, for example, for super Yang-Mills theory, dual to type 2B, say ADS5 times S5, the duality is very rigid. Okay, there's no room for average. So it's there's significant difficulties. So when you go to more realistic gravity theories. And so there are two logical possibilities to go around this problem. One is that actually the gravity expressions also factorize. And means that when you do gravitational path integral, you actually miss some fundamental contributions, even in the G-Newton goes to zero limit. Okay, so here, I emphasize here, we are talking about G-Newton goes to zero limit, which we believe that the semi-classical expansion is valid. And if gravity expression has to factorize, and then that means the standard semi-classical expansion, which has been so successful, must break down in a fundamental way. Okay, and we haven't seen any indication of that. And also for the gravitational expression to factorize, that will also destroy the success of the page curve people have used, say, for the last number of years. Anyway, so this is the first logical possibilities which we don't see much evidence for. And the second logical possibility is that some kind of average or constraining are needed to mapping the CFT to gravity. So this is a very reasonable idea. So it's that what gravity calculates, so you modify the dictionary to the following. So you say, in order to address this factorization problem, you modify the dictionary. You say the gravity partition function, what calculates in the G-Newton goes to zero limit, is some kind of cross-grained or averaged CFT quantities. Okay, and because you are doing some kind of cross-graining, you are doing some average, so the left-hand side does not have to factorize, then you address this factorization problem. But at the current stage, the gravity result actually has been used as a definition of this bar here, okay? And there's no intrinsic boundary definition of what this average means on the CFT side. Of course, there has been many attempts trying to define such averages in different series. say people have tried average of Hamiltonians, CFT data, states, observables, or the rank n, etc. And so and they have achieved a lot of very promising results in relating the average CFT quantities to the gravitational path in the group. Okay. But there are also many challenges in this direction. So first, as I mentioned, for those duality related to coming from string theory, there's no lateral ensemble exists. So there's no lateral ensemble which for super Yang-Mills theory belongs, or there's no lateral ensemble which this symmetrical orbifolds say, yeah, this the D1, D5 strings, D1, D5 world volume theory of D1, D5 system and exists. Okay. Anyway, so if you want to do some kind of average, since this relation between CFT and the gravity is so fundamental and so foundational, you want whatever procedure you use to define their relation to be a universal one. You cannot be say, oh, I have a procedure for some two-dimensional CFTs, but then now I do a different procedure, say for super Yang-Mills theory, and then I have another procedure do a ABGM theory. Okay, so that cannot be a fundamental solution. A fundamental solution must be universal, and it's because this is such a fundamental relation between the CFT and the gravity. And so this is the first challenge. And the second challenge is that on the gravity side, there's this asymptotic expansion. On the CFT side, we also assume there's asymptotic expansion which maps on the gravity side. And this Lorentzian asymptotic structure actually may not depend on how you do the average. This Lorentzian asymptotic structure may not be preserved by the average. Okay, so when you do the ensemble average, even though maybe each theory, say, have a Lorentzian expansion, but when you average this Lorentzian expansion, and then the averaging procedure and the Lorentzian expansion, they may interact non-trivially. And so that will cause difficulties. For example, say one idea is that you can average over n. And when you, for example, when you average over n, maybe you can preserve some leading structure. But if you want to preserve the full Lorentzian asymptotic structure, actually it's very, very difficult and may not be possible. Okay. And the third is that there have been already many successes in mapping from the boundary theory quantities to the gravity calculations. For example, the Wilson loop calculation in the for super Yang-Mills theory and various quantities in ABGM, etc. So all those precise Bach boundary matchings rely on specific system. Okay, when you do the average, and then you just destroy that kind of matching. Okay, so whatever average you do, not only has to be universal, but also has to really preserves our current success, which are based on non-average theories. And lastly, which is also a fundamental challenge, is that one of the fundamental feature of the holographic duality is that we can understand the unitarity of the gravitational side from the unitarity of the CFT. But now if CFT and the gravity are related by some ensemble average, and then you know that even though each CFT may be unitary, but when you average different CFTs, and you no longer get a unitary theory. Okay, so that would imply the gravitational theory actually is not unitary. And so that would be deeply troublesome. Okay, and so even though there have been various successes in relating averaged quantity on the CFT side to the gravity side, there are many, say, technical and conceptual challenges. So this is one problem. And actually, there's another problem which makes this relation not as, cannot be correct. And so this problem is what I call the erratic n problem. And this problem actually has not been really emphasized in the past. It was hinted in the paper by Schenkler and Schenecker and Witten in 2022. And in the paper of last September, I tried to emphasize this problem more. So the problem goes as follows. So on the gravity side, in the Lorentzian limit, we define the Lorentzian partition. We define the gravitational partition function through a path integral, gravitational path integral, by doing, say, side point approximation, etc. And so one features of this gravitational path integral is what we normally call the Picard-Lifshitz form. Is that the G Newton appears as the coupling constant in the prefactor in the exponential, and then the metric or the matter fields and the action and nothing else depends on G Newton. So this has a very specific structure. Means that when you take the G Newton limit, when you take the side point approximation, then you have a very specific structure you obtain. Okay, so you obtain the leading term from the exponential, the side point, and then you can get one loop, two loop, etc. And then you sum over all possible saddles. Okay, so I, which you sum all possible saddles, which satisfy the same boundary condition, say as M, specified by M. Okay. So this has a very specific structure, and so this is, and it's a very constrained structure. Okay, so this is normally called the trans series. So not only, so actually different side points, they're actually not independent of each other. Say, for example, the higher, say, subdominant saddle point actually can be deduced from the perturbative expansion of the leading saddle, etc. So this all these resurgence phenomena, etc. So this is a very tight structure which comes from the specific structure, say, of this gravitational path integral. So I will refer to this behavior, which can be expressed in terms of a trans series, as the smooth behavior in G Newton. Okay, so this depends on G Newton in a very specific way, very constrained, very specific. Okay, and you have all this resurgent structure, etc., in the G Newton expansion. But on the CFT side, we don't have the same structure. So the CFT partition function normally have the following structure. So you integrate over your CFT fields, say, for example, the incremental super Yang-Mills series or the Yang-Mills fields and the scalar fields, and then you have the action like this. So when you scale in the 't Hooft limit, you can take the scale out the factor of n, but this path integral depends on n in a rather complicated way. First is that the field you integrate over depend on n in a non-trivial way. They are n by n matrices. Okay, and the trace also, of course, depend on n in the depend on n in a rather non-trivial way. Okay, so this CFT partition function, when you take n go to infinity limit, actually depend on n in the highly non-trivial way, which is not in this standard Picard-Lifshitz form, which give you a trans series. Okay, it's just not of that form. So n in the boundary CFT is just not just a coupling, but also characterize the number of degrees freedom. Okay, so come into the rank of the phi. So normally we just made the assumption. We say, oh, maybe when it's just based on the 't Hooft expansion perturbative, say, Feynman diagrams, and based on very limited CFT calculations, and we normally assume that the CFT partition function, when we take the n go to infinity limits, have what we call smooth form. And again, you said you can expand in some kind of the trans series. Okay, so our normal CFT Lorentzian expansion, we assume they always have this kind of structure. Again, you sum over the Lorentzian saddle point, and then this is the one loop contribution. This is the leading one of n contributions, higher order one of n contributions, etc. And you sum over all possible subdominant Lorentzian saddles. Okay, So we have been, yeah, for example, in the anchor for super Yang-Mills theory, for Hawking-Page transition, you can show this explicitly. Okay. But in general, given that this CFT partition function don't have this Picard-Lifshitz form, so there's no reason, okay, this is always true. Okay, so the question is that what would be the most general structure on the CFT side? Would be, it's not obvious this will be always true. Okay, and if this is not the case, and then the gravity on the CFT side, then they don't have the same structure. So the gravity side always is expressed in terms of a trans series, but the CFT side, there's no reason should be expressed in terms of a trans series like this. Okay. Again, if the CFT side can be expressed in terms of a trans series, and then we say it depends on n smoothly, has smooth behavior in n. Okay. And so, yeah, again, this is the, yeah, so this is another problem which I call erratic n problem. Okay, so the purpose of the talk is that I want to make a simple proposal to address both problems. Yeah, by the way, if you have questions, don't hesitate to interrupt me at any time. So is there any questions so far? Good, okay. Then I will continue. Okay, so now the proposal is the following. So let's imagine we can calculate the CFT partition function in a large limit exactly. And now imagine it in general cannot be written just in terms of the trans series. Okay, and then we can just naturally write it in the following form, that the first term corresponding to a trans series in 1 over n squared, and which I call smoothing n. Okay, and then the rest, we just say, we just collect the rest which cannot be written as a trans series. We call it erratic in n. Okay, so as I mentioned, this depends on the smooth part depends on the very specific structure, very constrained, tight, specific structure. So anything else which is not in that kind of structure, we call them erratic. Okay, so right now we define the erratic by what it is not. Okay, and we know how to define the smooth part precisely, and the erratic part is just anything which is not of this form. Okay. Yeah, anything which is not this form. So for example, the erratic part can depend on, can have some kind of phase dependence, yeah, some kind of n-dependent phase, which cannot be written as some kind of saddle point. And then that would be one example, say, of erratic n-dependence. But there may be many, many other kinds of erratic n-dependence, which yeah, n is an integer, and so there in principle can be many okay different kind of erratic dependence. So the new dictionary I propose is that we just take the smooth part of the CFT partition function, the part which you can write as a trans series, and then identify that part with the gravitational partition function. It's because the gravitational partition function by definition is a trans series. And so in other words, to match the CFT expression with the semi-classical gravity one, we need a filter. We need to filter this out the smooth part of the CFT partition function. Okay, and the filter out, get rid of this erratic part. So this is what I call a filter. Okay, and this filter should be intrinsically defined, provided that this split is well defined. Okay, and this split is this split is in principle well defined. It's because we know how to define a trans series precisely. So there's a precise mathematical definition for a trans series, And so in principle, this is also well defined. Okay. But of course, in practice, it's very hard to calculate, to do the separation. But here I'm talking about in principle, just conceptually, and we should be able to make the separation.
Sorry, Hong.
Yes.
Shouldn't the Lorentzian limit be part of the filter? Because maybe you do something funny with the Lorentzian limit that provides you the filter? Like this proposal with a Mellin transform and so forth?
Yeah, so that's what has always been the assumption, right? So what has always been the assumption for many years, people just assumed somehow Lorentzian limit automatically acts as a filter. Okay. And so that's what people have been assumed for the last 2 or 3 decades. But now I want to question whether this assumption is actually the correct one. And we have seen some indications. And just now we have more, just from the CFT partition function, even when you take Lorentzian limit, there's no reason, okay, you will get the smooth behavior. Because even the Lorentzian limit, the partition function is not in the form which give rise to the trans series. Okay. So,
sure.
Yeah.
Yeah, I'm just asking. I completely agree with what you're saying. I'm just saying that maybe the filter involves some funny way of taking the Lorentzian limit.
Oh,
so,
I mean, a Lorentzian limit is a Lorentzian limit. It just once you do some funny way, and then you're doing some kind of filter. Okay, here you just suppose you just do an honest calculation. CFT at finite n, take the Lorentzian limit. And now we ask, let's take this quantity, let's try to separate what we can characterize as a trans series, and the rest is called the erratic part. And there's no, just previously we just always assumed maybe only the smooth parts exist, but just doesn't have to be the case. And I will show, if you now make the assumption, somehow if you relax your assumption, okay, just imagine there is an erratic part, just with very simple this thing actually can buy us a huge amount, both technically and conceptually. Yeah. Good. Is this clear?
yeah. I agree with everything you're saying. I was just. I guess I was asking about a more technical point of whether. What does it mean to take the Lorentzian limit, even if it involves some sort of averaging, Mellin transform, whatever, is part of the.
No, Lorentzian limit is just a standard Lorentzian limit. Imagine we calculate n equal to super Yang theory at the finite n. You can get some, say suppose for example, you can calculate it at finite n is some explicit expression which depends on n. Just take the Lorentzian limit. Just this, the left hand side is a straightforward. N is a parameter. You just take a notch.
I agree with this. Okay, yeah. Thanks.
Good. So now let's say if something like this exists, then we have to do a filter in order to compare with gravity side. Okay. So just to summarize, the one-step proposal is that the filtered CFT partition function, okay, in the Lorentzian limit, is identified with the gravitational one. Okay. And so this then provides an intrinsic boundary definition of what people call the average. Okay. And which has been so far only defined through gravity. Okay. So now I give you an intrinsic boundary theory definition. And also because now we are doing the filter. Now when you do the filter for the CFT on the destroying the manifold, and now, as we will see later, because of the filter procedure, and actually the smooth part of the CFT partition function no longer factorized. Okay, so that will address your factorization problem. Okay, and so this will be a very key point, which I will elaborate in detail later. Okay. So now let me just list some properties of this filter. So these properties, in principle, you should be able to just deduce from this split. Okay. And so for example, so the first property is that this should behave like a projection. Okay, so if you act the filter twice, so if something is already smooth, of course, when you filter it, of course, you still get something smooth. So this behaves like a projection. And the second is that if you have a smooth quantity, say suppose A and B are standard trans series. Okay, by smooth, I just mean the standard trans series. So if you have something smooth, multiply something which is erratic, and then by definition, you still get something erratic. Okay. So in other words, when you do this kind of filter, and the smooth part doesn't do anything, just come out from the average. You can just factorize out. Okay. So this just follows from the simple definition which I already given before. And now here, right now I don't have a full control of that split. So the properties, the next two property will be my assumption. So is that I assume that the somehow the split between the smooth part and the erratic part actually preserves the complex conjugation. Okay, so if whether you do complex conjugation before or after should not matter. And so this is a very natural assumption. Right now I don't know how to prove it, but and the last the property is that they require the filter does not change the positivity of the filtered quantity. Say if the filtered quantity is positive, and then after you do the filtering, it should be positive. Okay. Again, this should be something in principle one can prove mathematically, but right now I don't know how to prove it. And right now I just assume it because that appears to be a very natural physical assumption. Okay. And now with just these simple properties, and then you can easily convince yourself those properties warrant that this filtering procedure actually does not suffer, okay, from the difficulties mentioned earlier for averages. And this is intrinsically defined in principle for any CFT and universally defined. And this will not destroy those agreements which we had for individual theory, because this is based on individual theory. Okay, this split is based on individual theory. You don't need to look at the ensemble of theories. You don't need to do any average. So this is based on individual theory. Okay, so all these difficulties associated with the averages, you avoid them. Okay, you avoid them.
Can I ask something? Sorry, it's probably a stupid question.
Yeah.
Property 3, what is the motivation for it?
Oh, property 3, just just say it's just very natural. Somehow you should not say if you have something real, and when you do the filter, you should not create something complex. Yeah.
I see.
Yeah, just it's a very natural one. I don't know how to prove it rigorously at this stage mathematically, but somehow one would expect somehow this split between the erratic part and the smooth part somehow should preserve this.
Can I ask a question?
Yes.
Yeah. So, are there some math results about the split between the trans series and the erratic part being unique? Like, can we write the same thing as two different time trans series and two different erratic parts?
Yeah. So, of course, this is really, I think, really as far as I understand, this is an open area in mathematics.
Mm-hmm.
So normally when people do this kind of a trans series, they start with this kind of integral of this so-called Picard-Lifshitz form. Mm-hmm. And so then that guarantee you just get the trans series. And or you look at some differential equations, you can just get trans series. Have not seen mathematicians really discuss somehow more general story. Yeah.
Mm-hmm. Okay. Thanks.
Good. Okay, so now let's go to the interpretation of the wormholes. So this not only give you an interpretation of this average, actually we can give you a prediction of the wormholes in some sense. So let's consider CFT, this CFT defined on some disjoint manifold M1 union M2. That by definition, they should factorize at finite n, and the Z1 corresponding to the partition function on M1, and the Z2 corresponding to partition function on M2. Okay. And then for each of them, we can do the filter. For example, if we filter Z1, and then that should be related to the gravity on M1. Suppose M1 is connected, okay, and a gravity partition function on the with boundary M1. And similarly with filtering on Z2. Okay. And now you do filter on Z1 and Z2, Z1 times Z2, okay, which is the CFT on the M1 union M2, then that should be equal, according to our dictionary, corresponding to gravitational partition function with the disjoint boundaries. Okay. So now here is the key. So now let's define, now let's just isolate the erratic part. Okay, so as I mentioned, we split any partition function in terms of the average, the smooth part, and the erratic part. Okay, so now let me call this erratic part for simplicity notation. Let's call it delta E. Okay. So by definition, when you act F on the erratic part, the Z1, you get 0. Okay, it just our definition somehow it's 0. But now here's the key. Okay, imagine you take the erratic part of Z1, say delta ZE1, and take the erratic part of the Z2. So this take the product of them. Okay, so now let's consider F1 Z1 times Z2. Okay, and then can be the written as FZ1 FZ2 and delta Z1 delta Z2. Here I just used this split, and I used the fact that when delta Z1 multiplies Z2, and you still get something erratic, and then the average becomes 0. So the cross term between delta Z and the F will be erratic to be 0. Okay. But now the key thing is that the erratic part of Z1 times the erratic part of Z2, their erratic part may cancel due to the product. Okay, so their product may actually have a trans-series expansion. Okay, even though each one of them may not. Okay, for example, if you imagine, say, delta Z1 have some kind of erratic phase in N, which cannot be written as a set point form. And now delta Z2 also have the same but the opposite phase. And then when you multiply them, then the phase cancel, and then erratic part, and then those erratic independence disappear, and then you may get something smooth dependence on it. So the key thing is that the product of the erratic part, they can actually generate, can in principle generate smooth part. And so now when we do the average on Z1 times Z2, now we have this factorized part corresponding to the disjoint partition function on the gravity side corresponding to, but then you can also have this non-factorized part. And then we can just equate the non-factorized part on the left-hand side with non-factorized part on the right-hand side, and then we just identify this quantity with the wormhole contribution on the gravity side. Okay, with the gravity contribution, with the wormhole contribution on gravity side. So in other words, if I call such thing as correlations among the erratic and dependence, and then that tells us that the wormhole on the gravity side, what they reflect are essentially just correlations. So among the erratic part of the different CFT partition functions. Okay. So this is just for the product of two. You can trivially generalize. Yeah. So this is just equal to the wormhole. So the wormhole captures is the erratic part on this manifold and the erratic part on that manifold. Somehow when they take the product, they have a smooth expansion, and that's the wormhole. And you can also generalize to multiple disconnected, say, wormholes, boundaries. Say you can consider, say, the product of the 3 partition functions, and then that can be related to this kind of wormhole. And then, yeah, so yeah, but when you have multiple one, then you can consider connected correlations or disconnected correlations, etc. Okay. And we can also generalize. So in addition to have these manifolds, you can also have some light operator insertions. So X just denotes some light operator insertions. You can insert operators on each boundaries. You can consider generating functionals, consider correlation functions, etc. And so the full boundary data is controlled by this M and X. Okay. So now just your CFT partition function, of course, depend on this full data, script X, okay, which include both the manifold and the operator insertions. And now you can generalize to arbitrary number of products. For example, the connected M product correlations on the CFT side then should be related to the wormhole, the connected wormhole between these n different boundaries. Okay. So as I said, in principle, on the CFT side, we should be able to define this delta E, this CFT intrinsically. So this relation just provides an intrinsic boundary explanation of this wormhole, okay, and actually give a prediction of the amplitude. So if I'm powerful enough to calculate such CFT partition function, then I can extract those delta E's. Then I can just do a symptotic expansion of their product. Okay, and then that way, then I can predict the wormhole amplitude on the gravity side. Okay, and so right now, of course, the calculating this erratic part on CFT side is very difficult. Okay, because we have somewhat limited power. Even if I give you a finite n CFT partition function, okay, to really take the large n limit of that finite n expression, etc., and isolate this delta E, may still be technically difficult. Okay, so yeah, but here is a conceptual thing. Okay, so this is not just actually. Yes.
So have we defined what purely from the CFT side what this connected part of this filter would be?
Oh yeah, you just take the product. And the product is some function, and then I just do a symptotic expansion of that. Again, the trans series is something. So the assumptions that give me any large n quantity, I should be able to isolate a trans series part from it. Okay. So the product is some kind of large n quantity, then I should be able to isolate the trans series part of it. And that part is the wormhole.
I see. Okay. Got it. Thank you.
Yeah. Okay, so this actually not only provides you with a conceptual way to think about it. Actually, I will now show you that this identification has immediate implications. It actually predicts an infinite tower of inequalities for the wormhole amplitudes. Okay, so now let's see how this works. So let's imagine. So remember this script X denotes the CFT data. Okay, so the boundary manifold plus possible operator insertions. Okay, and if you give me this boundary data, then in principle I can get the CFT partition function, which is a number, and then I can extract this I can extract the erratic part. Okay, it's also some number. Okay, And so I can view this thing, this erratic part, as a function on the space of all possible this boundary data. Okay, so now if I look at the product, and together with their complex conjugation, then they actually form an algebra. It's a commutative algebra. It's very simple, just a product of the functions. Okay, it's a commutative star algebra. Okay, so here we can allow complex conjugation. It's because you can say insert operators. You can insert complex operators. You can take Hermitian conjugate, etc. And you can also insert heavy operators even when you define the manifold. So in principle, the CFT can be CFT partition function can be complex. Okay. So this forms a commutative algebra, and then this filter act on this commutative algebra, then give you something smooth part. Okay, here by C I just means the smooth part. Something smooth, a trans series. Okay, here actually I should use a different notation rather than C. I should call this the space of a trans series. Okay. So this F map this algebra to some fields. Okay, some space. Okay, some mathematical space. And by definition, this means a state on A. Okay, so algebraically, a state on an algebra it's a mapping from the algebra, okay, into some kind of into a constant, and from the erratic function, the constant is just the smooth part. Okay, remember the field does not do anything to the smooth part. Okay, so this filter actually defines a state on the algebra. So if you have a algebra, if you have a state, and then this state satisfy these properties which are given earlier. So the state will satisfy the property which we discussed earlier, following from the filter F itself. Okay, and then that actually leads to a Hilbert space. Okay, so this is standard GNS construction. Give me an algebra and the state, I can define a Hilbert space. Okay. So heuristically speaking, the Hilbert space, each state in the Hilbert space corresponding to element of this algebra. Okay, so for example, delta E CFT corresponding to a vector on this state. You can also take the product, say, of two such CFT erratic partition functions, and then that gives you a vector corresponding to the product of this, yeah. Anyway, just each algebraic element, you can imagine heuristically that map to some vectors in this Hilbert space. And the overlap between those vectors just given by this state itself, just given by this the state which is just the right now is just a filter. So this gives a Hilbert space structure, okay, for the space of these functions, okay, of these erratic functions. So this is a well-defined Hilbert space because of this F have this property which I mentioned earlier, that F maps positive quantities to positive quantities. Okay, so that means that this this is a well-defined Hilbert space with the well-defined inner product. And in particular, there's a Cauchy-Schwarz inequalities between the inner product of your states. And now you can just immediately see, and this will lead to some inequalities. So this wormhole amplitude corresponding you transition from X, the overlap between X and X prime, and this wormhole amplitude corresponding to X, and this corresponding to X prime to X prime. Okay, so this is just standard Cauchy-Schwarz relation. Okay, and so we see this thinking is very powerful. Okay, so immediately tells you that somehow whatever theory you have, gravitational theory you have, if they have a CFT dual, then their wormhole amplitude should satisfy this constraint. Okay, and this is also provide a way to falsify our assumption. Okay, so if this is checked not to be correct, and then there's something wrong with my proposal. Okay, so that's the nice thing about the proposal is that on the gravity side, you can in principle check it explicitly. So I should mention the similar inequalities has also been considered by this group, and which their motivation was purely from the gravitational path integral point of view, and it's just some desirable properties which they want the gravitational path integral to satisfy. And then they actually checked this in many examples. And at least from what Luca was telling me in December, and they all worked. Okay. But not only you have this kind of inequality, but you actually have infinite number of them. So you can consider the states which corresponding to products, say, of such kind of partition functions. For example, you can consider the state corresponding to the product of the x1 and x2 partition functions. And then the x1 and x2 states overlap with x3, then should be smaller than the x1, x2 with itself, and x3 with itself. Okay. So just by choosing different states and using Cauchy-Schwarz, you can just get infinite tower of the inequalities constrain all kinds of the wormhole amplitude. Okay. And so this is a very powerful prediction. Okay. And so actually, this Hilbert space structure is actually not just some mathematical device. And actually below, I will interpret this Hilbert space as the semi-classical Hilbert space of all isolated closed universes. Okay, so just to summarize what we discussed so far, let me just make some remarks. Okay. So the first remark is that let's start this finite n partition function, this finite n holographic duality relation, which we believe still should be correct. Okay, and just you calculate your CFT partition function as some n equal to 100, and you map to your quantum gravitational partition function as some value of G Newton. Okay, so this still, we don't see any indication that this equation breaks down. Okay. But now if you want to consider the semi-classical regime, then you need to do filter on both sides. So on the gravity side, normally we don't talk about the filter. It's because we already have been using gravitational path integrals as a semi-classical approximation. Okay, so effectively what the gravitational path integral and the saddle point approximation of the gravitational path integral does for you, for general theory, okay, is just do a filtering. Okay, but just we have been doing it all this time unconsciously. Okay. And so now what we are emphasizing is that on the CFT side, we have to do this filter. And then I provide a way how you define this filter. Okay, how you define this filter. So the fact that in the gravity side, when we go to gravitational path integral, we are doing some filtering also actually, in some sense, we should have already seen it's because in the full quantum gravity, G Newton also not only plays the role of the coupling, but also controls the number of degrees freedom. Okay, even though in the gravitational path integral, G Newton only appears as coupling constant, seems like nothing else depends on the G Newton. But we know, if you believe the quantum gravitational interpretation of the black hole entropy, which is area divided by G Newton. And if that quantity captures the number of degrees freedom in quantum gravity, then G Newton has to capture also the number of degrees freedom in quantum gravity. Okay, it just that is not manifest in this kind of gravitational partition function calculated, say, from the path integral. Okay. And so we actually have been interpreting G Newton to control the number degrees freedom when we try to give some quantum gravitational interpretation of the semi-classical quantity. Okay. So the second remark is that this split, so here I postulate to be, say, should be a mathematically well-defined one and unambiguous. But right now, we still need to develop mathematical machinery to really explore this structure. Okay, so mostly people have been exploring the trans series, but people have not really been actually exploring this erratic part. Okay, even just biological possibility should be there. Okay. And of course, the explicit calculations of the CFT partition function at finite n, and then we take large n limits and really do this procedure carefully, of course, will be extremely valuable. Also, I want to emphasize the picture I'm proposing here is fully consistent with the discussions using various averages. Say people, yeah, there are too many people, there are too many papers which I didn't cite, etc., which I cannot really cite here. So there have been many papers which people discuss various kind of averaging procedure on the CFT side, then they compare with the gravitational partition function, the gravitational result. Okay. So there's no contradiction between our pictures. So what this kind of average does is the following. For specific systems, for specific CFTs, for specific questions, it may be easier to use specific averages to extract this quantity. Say, as far as if I have a procedure, say, to get rid of this erratic part, for specific problem, then I have extracted this smooth part. Say, if you can average over your OPE coefficient to get rid of this erratic part, then that's great, okay? And then we have extracted, then we have effectively extracted the smooth part. And similarly, yeah, you can use some other averaging procedure. So the averaging procedure itself does not have to be universal. Okay, so this structure is universal and fundamental, but the average procedure can be used for specific systems, okay, for specific questions. And in particular, there may exist multiple different averages to extract the same quantity. Okay, so this is a little bit like in classical statistical physics. You do cross-graining, okay, to get thermodynamics, etc. And the cross-graining, the details of cross-graining is not important. Okay, different cross-graining procedure can give you the same result, universal results. But cross-graining itself does not tell you the fundamental structure. Okay, you need the fundamental quantum statistical physics or classical statistical physics to tell you the fundamental structure. But the cross-graining is a way to extract the universal answer. So here is the same thing. Okay, so the kind of average people have been doing, they just corresponding to different procedures of to extract these kind of universal quantities. And so here our proposal is just to provide a conceptual and fundamental and universal way to define these quantities, and why actually your averages can work. Okay. Good. Any questions on this?
Does this somehow assume that the erratic and smooth separations are unique?
Yeah, so right now I cannot answer this question for sure. I can imagine, so they don't have to be unique. So as far as they separate qualitative physics will be fine. Say, for example, maybe another analog in mind is that in quantum field theory, say when we do realization, we separate the finite quantities and the divergent quantities. And that separation, of course, is physically and mathematically meaningful, but the separation is not unique, and it depends on how you define your finite part. And so this is a little bit similar to that. And this is a little bit similar to that. I can imagine maybe there's some ambiguity. You can define the smooth part, and you can say group some erratic thing into smooth part, etc. Yeah, anyway, there might be some kind of reshuffling between the two, similar to this kind of realization group structure maybe we see in the realization. Yeah, yeah, of
But I
course,
guess
right
then
now, I
the,
don't know.
yes.
I'm just offering a logical possibility. Yeah.
No, I'm just trying to see whether, because there you make a statement that essentially like if you had an some kind of average, basically, I guess any observable will be it would be irrelevant for an observable that you could measure in principle in the field theory, whether you take a large N, this filter procedure, or any kind of average over coupling, for example.
Yeah, right.
Okay.
Yes, I would imagine, say, if you want only interest in the leading order in a large N limit, say not to the all orders, not to the all subdominant behavior, and then I would think this separation should be rather unambiguous, and just as people already did in when they do various the ensemble average procedure, and the ensemble average also gets tricky when you go to higher orders. And so if you want to define this separation to all orders for all subdominant terms, I don't know. Right now I don't have full mathematical control to make any definite statement. But yeah.
What would be the, sorry, I mean, this might be a stupid question. What would be the minimal ingredients that you need to make a toy model that could possibly predict out of this? Presumably you need at least a matrix model or something like that.
Yeah, so it's actually, I'm going to mention some of this thing a little bit later. Yeah, yeah.
Okay, good. Thanks.
Yeah, provided I have time. So let me see. I think I'm already running out of time. Yeah, let me just very quickly mention the Lorentzian signature. So far I've been talking about the Euclidean. So in the Lorentzian signature, the story is actually richer. So let me first talk about the conventional wisdom. So conventional wisdom is that when, say, if I give you a Bach Lorentzian manifold M, then we normally say, this should be dual to some sequence of states on the CFT side. Then when I take the large N limit of sequence of states, then that is described semi-classically by this Bach Lorentzian manifold M. Okay, and then the observables in psi n, when you take n go to infinity limits, say correlation functions, entanglement entropy, all these things, and then can be extracted from semi-classical gravity quantities from this manifold, based on this manifold M. Okay, so this is our standard dictionary for the Lorentzian case. And also we can ask the question in the converse way. So if I give you a sequence of boundary states, okay, then how do we know that it actually has a semi-classical gravity description? Okay, and so normally we go from the gravity side to the CFT side. If you have a gravitational manifold, then there must be some kind of CFT states dual to it, okay? Just from the duality. But now if you want to ask opposite, okay, so how do we know you have a semi-classical gravity description? So this is the question of emergence. Okay, how do we define the emergence of the box space-time from the boundary theory? Okay, and so what we have? So a working definition which we have been using is the following. Let's consider the connection of all possible single trace operators. It's because below the single trace operator, they have a well-defined large N limit themselves. You can define them in an n go to infinity limit without introducing any additional machinery. So they are fundamental. Okay. So we look at all the single trace operators, and then we look at such correlation functions of single trace operator between the sequence of states. And then we take n go to infinity limit. So if this n go to infinity limit is well defined, okay, then at least this is a necessary condition for the emergence of some kind of box space-time due to this sequence of states. Okay, and if you say, oh, maybe there's a Bach semi-classical gravity description. So this is what we normally define using the standard picture to define the Lorentzian emergence. But now with our new Euclidean dictionary, so clearly this kind of Lorentzian dictionary and also the Lorentzian, the definition of Lorentzian emergence should also be modified. Okay, but this is easy to do. So suppose we have some Lorentzian observables, Gn in some states psi n due to some Bach manifold. And again, we can look at n go to infinity limit, and then we can separate this Gn into smooth part and the erratic part. And then we just define the filter to, again, just extract the smooth part, and then we identify that with the semi-classical gravity result. Okay. Again, by definition, a semi-classical gravity result was defined from gravitational path integral. They only contain smooth dependence. They don't have erratic behavior. And so that also gives rise to a generalized Lorentzian emergence, which I call filtered Lorentzian emergence. So if you can see the sequence of state psi, we say it has a semi-classical gravity description if now the filtered correlation function, okay, of single trace operators are well defined. So this is a very important distinction. Okay, in principle, say if this psi n have some erratic independence, this kind of single trace correlation functions may have erratic independence. Then when you have erratic independence, then you don't have a well-defined Lorentzian limit. And then from the standard emergence, this cannot lead to semi-classical geometry. Okay. So here I relax the definition. Is that you only need to have a smooth part, and the smooth part to be well defined. Okay. And so I will show actually the examples of this emergent Lorentzian filtered Lorentzian emergence include the closed universes and the black hole interiors. Okay, so actually, yeah, of course, the here I just give you general introduction. In principle, I can finish the talk now. So let me just mention, if I say, suppose I have an infinite amount of time, what I would do. Okay, say just based on these conjectures between the just based on this proposal between the Euclidean Euclidean wormholes and the erratic parts of the CFT partition function. And now just using wormholes, now we can make conjectures on the erratic independence, say, of Euclidean partition functions. Okay, so let me just mention some, so I will not have time to really talk about it. Let me just mention, say, some places you may look for such kind of erratic independence. Is that whenever on the CFT side, if the CFT partition function involve OPE coefficients, okay, OPE coefficients of the black hole-like state, okay, then that is in general a place this erratic independence can appear. So the examples include, for example, in 2D CFT, if you can see the genus 2 partition function. So the genus 2 partition function, they can in principle, when you write it in terms of the OPE sums, then they in general involve the OPE coefficients of the Ivy state. And then that gives you a source of erratic independence, etc. Anyway, so you can make various conjectures, and then in principle, we can check them from CFT calculations, okay? And also, so the examples of filtered Lorentzian emergence are closed universes. Here, actually can separate into two types of closed universes. One type are isolated universes. Just the full space-time does not have a boundary. And there's another type corresponding to closed universe is entangled with ADS. So even though both type of, say, both type of space-time involving closed universes, at the closed universes in these two type of space-times actually are fundamentally different. So in the first type, you just have closed universes. There's no boundary, okay? So in this case, the closed universe, they cannot correspond to a finite n CFT state. Okay, so they purely have to be emergent, okay, from some kind of CFT structure. So there's no CFT states actually describe this kind of closed universe. But those closed universe do have a big, yeah, in the semi-classical limit, they do have a big Hilbert space. Okay, they don't have one-dimensional Hilbert space. They have big Hilbert space. They have standard semi-classical Hilbert space. But in the case of closed universe entangled with ADS, in those cases, actually, in principle, you can have yeah, because now you have a boundary. Because the ADS part has a boundary. So in this part, actually, then then actually you can identify, say, a finite n CFT state with such kind of space-time. And then you can then show that this closed universe is actually arise from erratic behavior, Lorentzian behavior of this kind of states, okay, through this filtered Lorentzian emergence, which I mentioned earlier. And also you can actually show that the black hole interiors. Okay, so we always have been suspecting that somehow black hole interiors are different from outside conceptually. Okay, so the wormhole or the firewall was one way to try to attempt at this kind of showing that somehow black hole interior is different. But by now we I think we have agreed that for many black holes there's really no wormhole at the horizon. But here I'm advocating something a little bit weaker. Is that the black hole interior actually come from this kind of filtered Lorentzian emergence, and in particular the black hole interior are what we call the quantum volatile. Say there's some kind of order one fluctuations, etc. Okay, so I think I'm already way over time, so I can stop here. Yeah.